We know that we can convert alkenes to alcohols by acid-catalyzed hydration, but we know that the carbocation intermediate in this process results in rearrangements. For example, this simple alkene with the tert-butyl group rearranges via a methyl shift to give this alcohol. Emphasized in red is the methyl group that moved. What if we wanted the alcohol that resulted from no rearrangements occurring and starting with the same starting material? That would be this. It turns out acid-catalyzed hydration won't work, at least not with that starting material. Side note, if you have a whiteboard, don't clean it with simple green. Use rubbing alcohol. So if we want to go from an alkene to an alcohol without rearrangements, the reaction we want is oxymercuration reduction. The first part of this two-step process, oxymercuration, involves mercuric acetate, which is mercury 2 with 2 acetate groups. This is an aqueous solution. The second part, as you may have guessed from the name, is a reduction. We use sodium borohydride in a basic solution. Together, these two steps give us exactly what we want, an alcohol from an alkene with no rearrangements. I'll emphasize the new hydrogen in green. This came from sodium borohydride. In other words, it came with its own electrons in a reduction, as opposed to an acidic hydrogen, which takes a nucleophile's electrons. Let's examine the mechanism. First of all, we have mercuric acetate. This may well be your first time seeing a reaction involving a transition metal. If so, just bear with us. It's a little strange, but I'll explain it. The mercury accepts the 2 pi electrons from the bond. At the same time, it donates 2 of its own electrons back to the newly empty p orbital. When this happens, 1 acetate group leaves. The result of this addition is this, what's called a Mercury Neum Ion. Essentially, it's a mercury added across that double bond, with 1 acetate still attached. This Mercury Neum Ion has a partial positive charge on that secondary carbon. The reason this Mercury Neum Ion carries some partial positive charge on that secondary carbon is because hyperconjugation from the group next to it stabilizes that positive charge just a bit. So occasionally, the positive charge resides on that secondary carbon. On the primary carbon, those 2 hydrogens sticking off of it don't have any sigma bonds that can overlap in any way and stabilize a positive charge there. So being mindful of this partial positive charge on that secondary carbon, with water as our solvent, it comes in and attacks as a nucleophile via backside substitution on that secondary carbon. It's a secondary carbon here, but it could be a tertiary carbon if we had a different starting alkene. This addition gives us this as a product with a water group added there and the acetoxy-mercury group still attached via 1 bond. Now keep in mind we have an acetate in solution hanging out, and there is a protonated alcohol there. Acetate will readily take that proton and give us this as our preliminary product, a product from step 1, along with acetic acid. Now keep in mind, hopefully you know this, that because acetic acid's pKa is 4.7-ish, and a protonated alcohol has a pKa of -2, this acts as an extreme driving force to the right. So that's it for step 1 of this 2-part reaction. Here's our product from step 1. We're going to call this our oxymercuration adduct. There's a 1, there's a 1. See, look, emphasis. This is our product from step 1. Now we're going to talk about what happens in the presence of NaBH4, sodium borohydride. Hopefully you know the actual structure is something like this: sodium plus, borohydride minus. The crucial part about borohydride is that hydrogen is more electronegative than boron. This is a big deal. This means BH bonds have electron-rich hydrogens. Whenever we encounter this, keep in mind those hydrogens want to put those extra electrons somewhere. So these electron-rich hydrogens are unusual. They give up these electrons readily. Here's the important part. They reduce other species in the process. Sodium borohydride is one of the most common reducing agents. So what specifically gets reduced here? It turns out the mercury does. It goes from mercury 2, and here's how we know it's mercury 2. It's bonded to a carbon and an acetate group. Now if you broke that carbon-mercury bond and gave the electrons to carbon, it would have a -1 charge. If you did the same with acetate, the acetate would be a -1 charge. Overall, this entire molecule is neutral, so mercury must be +2. Now when we reduce mercury in a general reduction, let's say, it becomes mercury 0, and the down arrow means reduced, as opposed to oxidized. So we know our reducing agent will reduce mercury 2 to mercury 0. You may be curious as to how this last step occurs. I kid you not, my textbook says we won't consider the mechanism of this reaction. It was also not covered in my lecture. So, if you are really curious as to what happens here, either Google it or take inorganic. Try and stay awake. All you need to know is a C-mercury bond becomes a CH bond. Lastly, here's a balanced equation. So 4 oxymercuration adducts plus 4 hydroxide plus 1 sodium borohydride. Notice that 1 borohydride can reduce 4 oxymercuration adducts. Gives us that stuff. That is the same thing as what I drew here. That's our product. Most important thing you need to know about oxymercuration reduction. Markovnikov-like regioselectivity without rearrangements. Hooray. But what if we wanted anti-Markovnikov selectivity from the same starting material? Ooh, stay tuned.